Hi, this video is on breadth first search. We've covered depth first search in the previous two videos. Now we're going to look at the natural alternative, which is breadth first search, or BFS. So again, breadth first search, we abbreviate that BFS, it's an acronym, and it's a graph traversal, so we start at a start vertex and visit every vertex in the graph one by one in a defined order. The breadth first search idea is that you first visit the start vertex, then visit all the vertices one edge away from the start, then all the vertices two edges away from the start, then three edges away from the start, and that pattern continues until you've visited every vertex in the whole graph. We could make an analogy to a spiral search pattern, when they're doing an emergency search and rescue thing. They start at the best guess of where the person is, and then they use this increasing radius spiral approach so that they check the area near that location and then a little further away and then a little further away and so on until they find them, hopefully. So that's kind of the idea of breadth first search. Now, with depth first search, we started with a recursive algorithm, which was pretty clear, and then converted that to an iterative algorithm. But a recursive breadth first search is pretty challenging. It turns out to be difficult to implement that one away, two away, three away sequence using recursion. So we're going to skip directly to an iterative version of breadth first search. And it's actually pretty similar to iterative depth first search. We do need to change things up to get a different order of search or traversal. And again, we're going to need an explicit data structure to keep track of the unexplored vertices. And that's where the major change is. In breadth first search, it makes sense to use a queue for these vertices. In depth first search, we used a stack, because the idea of depth first search was, fly as far away from the start as you can, and then if you get stuck, just back up one step. And so that idea of just back up one step to where I just left off, that naturally fits a stack LIFO order. But with breadth first search, what we want to do is in an orderly fashion, visit everything one away, and then when we're done with that, everything two away, and then when we're done with that, everything three away. So that naturally fits the first in, first out queue ordering of first everything close, then everything a little further away. So in breadth first search, we're going to use a queue, not a stack. So we have two variables to keep track of the process of the traversal. A lot of this is very similar to depth first search, so we can go through this kind of quick. There's a scene vector, which works exactly the same way. It's a vector of booleans, and scene of v is true if v has been visited. That's to keep track of which vertices we've already visited so that we don't try to repeat the same vertex and get stuck in some kind of infinite loop. And we've got a to-do variable. This time it's a queue. I highlighted that. It's not a stack anymore. We have a queue of vertex indices that need to be considered. It's still kind of an inbox of vertices to process. So if a vertex still needs some work, it goes in this to-do queue. And the algorithm just keeps running until the to-do queue is emptied out. All the work is finished. Kind of the idea of this queue is it's the list of vertices that are further away from the start. So we're at the start, we've dealt with some of the vertices in the search, and then there's another layer that's further out. This queue keeps track of the vertices that are further away. They're one edge further away than the ones we've dealt with, but we haven't got to them yet. We have the same invariant that a vertex v is in this to-do queue if it's reachable. And that means a vertex in the queue might have been seen, might not have been. We're not sure. So here's the pseudocode. Again, there's a strong resemblance to depth first search, but it is different in a few details. So to begin with, you set up your scene vector of booleans. It's n false values. We create an empty queue of ints because we're using int to represent a vertex index. The first thing we do is visit start, set start scene flag to true, and add start to the queue so that next we'll look at all of the vertices adjacent to the start. And then while the work queue is not empty, while to-do size is positive, then we grab the front of the queue. It's not the top of the stack, but we grab the front of the queue. That's the next vertex to deal with. Remove that from the front of the queue. And then here's where the neighbors get added. So for every v in next's out edges, if we haven't already seen v, then we visit v and set v's scene flag to true. And then we add v to the to-do queue so that v's neighbors will get considered in a future iteration. So now let's run this on the same example we used with depth first search. We're going to do a breadth first search this time, starting at index number 3. So to begin with, we create the scene vector. It's the same thing here. So we've got n false values. Still 0 means false, 1 will mean true. And we create an empty queue called to-do. So over here, I've sketched my queue. The way that we sketch a queue is just a sequence of elements. The left element means the front. So to begin with, to do is empty. There's nothing in it. The first thing we do is visit start. I'm going to keep track of the vertices in the order we visit them here, just like we did before. So the first vertex that gets visited is 3. And we set 3's scene flag to true. See in the vector here, that's a 1, that's a true. And then add the start vertex, which is 3, to the to-do queue. So the queue has 3 as the one and only element in it. And now we go into the main work loop that repeats as long as the to-do queue isn't empty yet. So the first and only element of the to-do queue is 3, so next is 3. And we remove that from the to-do queue, so the queue goes back to empty again. And then for every out edge from 3, so there's an edge to 1 and an edge to 4, again, we're following this convention that will assume that out edges gives us 1 and then 4 in increasing order. So first we look at v being 1. V is not seen yet, so we visit v at this point and add it to the list and add v to the queue, because we need to look at v's neighbors in the future. So v is seen, it's in the visited list, and then that's 1. So the next iteration of this for loop looks at the other out edge of 3, which is 4. So now v is 4. 4 has not been visited yet, so we add 4 to the visit list and add 4 to the back of the queue. It's a queue, so we add to the back, and we set 4's scene flag to true. Okay, so the queue now has 1 and 4. So notice what happened here. First we visited the start, that's the start itself. Then we visited all the vertices 1 edge away. So this is the breadth first search thing happening. We did all of the 1 distance vertices. Now we're going to do all the 2's, which are the only 2 remaining vertices, 0 and 2. They're 2 edges away from the start. So the front of the queue is 1. So next is 1. And then we go through every out edge of 1. And if it hasn't been visited yet, we add it to the queue and visit it. So there's only one out edge of 1, which is 2. So now v is 2 in my loop down here. 2 has not been reached yet. So we visit 2, add it to the list, add 2 to the back of the queue, and then we're done with this loop. There's no more out edges of 2. So the front of the queue is 4. So now we take next to be 4, remove 4 from the queue. So 4 is taken away from the front of the queue. And go through the same loop for every out edge of 0. For every out edge of 4, there's only one of them, which is 0. So v is 0. We visit 0 and add 0 to the back of the queue. Okay, so at this point, we're at that same kind of juncture where, as a human being, I notice that we're done. We visited every vertex. There's 5 of them, and there's 5 on my list. The algorithm hasn't quite caught up to that yet. There's still 2 vertices in the queue that it wants to check to make sure that there's no more vertices to visit. So the next thing that happens is 2 gets picked as the next. It gets removed from the front of the queue. So here's 2 over here. And we go into this loop, but there's only one out edge of 2, which is to 3. And 3 has already been visited. If we look in the table here, that's true, and I recall doing that earlier. So 3 is seen. So this is a false if statement, and we don't do anything with 3. And again, that's important because that could trigger an infinite loop. If we visited 3 a second time, we would repeat this whole thing all over again. But 3 was the start. We already saw it, so we don't put 3 into the queue. And then the last step is that 0 is the front of the queue, so next is 0. We go through the same process, loop through every out edge of 0. There's only one of them, which is 1, but 1 is seen. So we don't do anything with that. We just skip over it. And now we're done.